the class. In this lecture we are going to discuss finite box potential. In the last lecture you have seen that we have discussed different aspects of a particle moving in an infinite potential box. So what we have learned in the previous class, so this was our infinite potential box where the potential was 0 between x is equal to 0 to x is equal to L, and particle was moving inside, and the wall were so rigid that particle cannot go out, so we can say that the potential is infinite at this point here and here. And so this is the potential. We have written that potential is 0 between x and L, and potential is infinite when x is greater than 0, or x is when x is smaller than 0, or x is greater than 0. And once we have solved the Schrodinger equation, this is the form of the wave function we have obtained. Phi n of x is equal to square root of 2 over L sine n pi over L times x, and this is the energy. En is equal to n square pi square h cross square over 2m L square. Okay, so we have seen that this energy is quantized because your n is integer quantity. Now instead of having infinite potential box, let's modify the problem, and instead of having the rigid boundary, we are going to have a kind of soft boundaries. Okay, so that the potential in this regime is V0, and in this regime potential is V0, and inside the box potential is 0. Okay, so this is we will call region 1, this is region 2 where potential is 0, and region 3 where the potential is again V0. Okay, so we can write down the potential in the functional form as Vx is equal to 0 between 0 and L, and potential is V0 when x is smaller than 0 or x is greater than L. Okay, so this is the modification in comparison to the infinite potential box, that the walls are not infinite and the potential is not infinite, but the potential is V0. Okay, so this is a one-dimensional finite box potential, or sometime also you will see that it's written as a step potential. Okay, now there are two regimes when we want to solve the time independent Schrodinger equation. One, the particle has energy E which is greater than E0, so this will be somewhere here. Okay, and another regime where the particle has energy which is smaller than the V0, so this will be somewhere here. And first we are going to solve this particular interesting one where energy is smaller than V0, and let's see what is going to be happen. Okay, so let's start with E is less than V0, and then we can see what are the corresponding boundary states. Okay, so in the region 1 we can write down the Schrodinger equation. Okay, because the potential is V0, so this is h cross square over 2m, second derivative of phi 1 with respect to x, where phi 1 is the wave function in region 1, plus V0 times phi 1 is equal to E times phi 1. Okay, now we can rearrange this equation and put right hand side 0, so that we can write the whole equation into this fashion, where the double derivative has no prefactor and nothing, plus 2 times E minus V0 over h cross square times phi 1 of x. This kind of things you have seen when we were solving free particle equation. Okay, now in region 2 this term is 0. Okay, so in region 2 we can write down the same equation with V0 is equal to 0, and we are going to say that the wave function in the region 2 is phi 2. Okay, so this is the equation for the region 2, and for the region 3 again we will get the same equation like this one. The only difference is that now instead of phi 1 we will call the phi 3. So these are the three wave function in three regions, 1, 2, 3. Corresponding wave functions are phi 1, phi 2, phi 3, and these are the corresponding time independent Schrodinger equation. Now we have to solve these three equations. Okay, so for region 1 we have to assume this part is equivalent to the lambda square. Okay, so let's say this is a lambda square, and now what we have considered, that energy is smaller than V0. Okay, so this quantity E minus V0 is going to be negative. Okay, so this is what we have written by substituting this one, and as we have done the general solution of this equation is written as m times sine lambda x plus n times cosine lambda x. Now if you want to recast into a different form this form of the wave function, what we can do, we can write sine and cosine in terms of the exponential. So this is what it's written here. So sine is written as e to the power I lambda x minus e to the power minus I lambda x divided by 2i, and cosine is written into this following function, e to the power I lambda x plus e to the power minus I lambda x divided by 2. Now we can rearrange the terms for e to the power I lambda x and e to the power minus I lambda x. So this will be the terms which are related to this e to the power I lambda x, and this is the terms which are related to e to the power minus I lambda. Now we can call these n minus im divided by 2 because these two are constant, so we can rename a new constant. So now we can call this as a and this as a b. So thus phi 1 of x is recasted in terms of exponential as a times e to the power I lambda x plus b times e to the power minus I lambda. Okay. Now in region 1, this is the one we have written in the last slide. Now remember, the definition of lambda square was 2m over h cross squared e minus v naught. Okay, as I said that e is smaller than v naught, so this is quantity is negative. Okay, so now we can redefine this quantity as alpha square, where this quantity now is a positive. Okay, so now we know what are the relation between lambda and alpha. So lambda and alpha will be lambda is equal to plus minus I alpha. Okay, so you can clearly see that this is the relation, because this will be negative, this is a positive quantity, and when we substitute, this will come out to be here. Okay, so now this whole thing can be written as a times e to the power alpha x, okay, and b times e to the power minus alpha x. Okay, so now these exponents are not anymore complex, but these are the real one. Now in region 3, this is the equation that we have written. Okay, and in region 3, as we have done for the region 1, we can write down the general solution of phi 3 as g times e to the power alpha x plus h times e to the power minus alpha x, where g and h are constant. Okay, and for the region 2, there is no v naught, so this is the equation that we have written, and the general solution can be written in terms of the k, where k is your 2m e over h cross square, and the general solution is written as phi 2 of x is equal to c times sine kx plus d times cosine kx. Okay, so these are the three wave function we have got: phi 1, phi 2, phi 3. Okay, and now we have to find it out what are these 6 coefficients. To find this coefficient, we have to first impose a condition that the wave function needs to be finite, means that when x goes to plus minus infinite, your wave function is supposed to go to 0. Okay, this is your asymptotic limit. Okay, so under this condition, okay, this part, because then this part will drop it out. Okay, so this will give you 0, because when x is smaller than 0 in this regime 1 or region 1, by using this x goes to 0 when phi goes to 0 when x goes to plus minus infinite, this imposes the condition that your b is 0. Okay, so your phi 1x is only a times e to the power alpha x. Now in region 3, this term will go to 0 by using the same condition. Okay, when x is greater than 0, it means that g is 0. So this gives us that phi 3 of x is h times e to the power minus alpha x. And in region 2, we have the same equation. Okay, that phi 2 of x is linear combination of sine and cosine functions. Okay, to find this coefficient, we have to impose another boundary condition, and this boundary condition says that the wave function at the boundaries, means at x is equal to 0 and at x is equal to L, should be continuous. What it means that phi 1 of 0, which is the wave function in region 1, supposed to be same as phi 2 of 0, which is a wave function in region 2, and this is at x is equal to 0. The same applies for another boundary which is at x is equal to L, that phi2 of L is equal to phi3 of L. So once we will apply this condition, let's see what we are going to get. Also, the derivatives of these wave functions supposed to be equal. Okay, so they have to be continuous. The same as the wave function at the boundary is supposed to be continuous, and their first derivative is supposed to be continuous. So this is the derivative of your phi1 at x is equal to 0 is equal to the derivative of phi2 at x is equal to 0, and the derivative of phi2 and the derivative of phi3 supposed to be the same at x is equal to L. Okay, so this is the phi1 we have written in the previous slides, and this is the phi2. Okay, now let's apply at x is equal to 0 boundary condition. So what will happen? This will once you put x is equal to 0, this quantity will be unity. So in the one side you will get a. Okay, in the right hand side you are going to get sine 0 is 0. So this term will go to 0 and d times cosine of 0. Okay, so this is the condition that you have got it, that a is equal to t. Now when you apply the continuity of the derivative of the wave function supposed to be the continuous at the boundaries, then if you take the derivative of this one with respect to x, what you are going to get? A alpha times e to the power alpha x. Okay, so a alpha times e to the power 0 is equal to, when you take the derivative of this one, it will be cosine, but k you will get it, and this will be a minus dk times sine. So this term goes to 0, this term will be unity. So what you are going to get? A alpha is equal to ck. So these are the two conditions that you have got from the boundary conditions at x is equal to 0. Now the similar boundary condition we can apply at x is equal to L. So the wave function in region 2 is this one which we have written in the previous slide, and the wave function in region 3 is only h times e to the power minus alpha x. So first condition, phi 2 of L is equal to phi 3 of L. So when you apply this, it will be h times e to the power minus alpha L, and here if you apply c times sine kl plus d times cosine kl, and when you apply the derivative, then you know what the derivative will come. It will be ck times cosine kx minus dk times sine of kx, and x is equal to L. So this is what you have got: ck times cosine kl minus dk of sine kl is equal to minus h times alpha times e to the 1 minus alpha. So these are the two conditions that you have got, and from the last slide we have seen that a is equal to d and a alpha is equal to ck. Now what we are going to do, these are the 4 equations we have, and these are the unknowns that we have. Okay, so 4 equations and 4 unknowns we have. Okay, so now the trick is that let's try to express all the unknowns in terms of a. Okay, so we know first d is equal to a. Now c can be written as alpha over k times a. So we have expressed d and c as in terms of a. Now so we have substituted the value of d here. We have substituted the value of c here. We have substituted the value of d here, and now h. So h is represented only in terms of the alpha. Okay. Now another equation that we have seen, that when we have to apply for the boundary condition in the region 2 and 3, this is another equation we have got. Now what we can do, we can just divide these two equations. Okay, so what we are going to get, this side we are going to get that alpha. Okay, so this equation divided by this equation. Okay, so what we can do, we can take this cosine. Okay, so what we can do, this cosine kl minus k times sine kl. Okay, and then we have written alpha cosine kl minus k sine kl divided by alpha times sine kl plus k times cosine kl is equal to minus alpha divided by a. That alpha divided by k, that you can see it. Okay, so now this equation is only having k, alpha. Okay, these are the two variables that we have. Okay, so this is what we have seen it. Now let's recall what is our alpha. Our alpha was 2m divided by h cross a square times v naught minus e. Okay, so now if we want to express everything okay, in one or another form. So let's multiply this 2m divided by h cross e square into this one. So first term will be this one, and another term will be 2m divided by h cross e square times e, where this 2m over h cross e square times e we have considered as a k when we were solving the equation for region 2. Okay, so this is our k square. Okay, and now this side we can see that this is nothing but c square minus k square. Okay, so this is what we have obtained. Okay, so now if we take the ratio of c over k, then it is easy that we can divide this quantity by k and this quantity by k, and we have already taken the square root. So this is your alpha over k, which is here written. We have represented in terms of square root of c over k square minus 1. Okay, and now this quantity we can call as f of k, or more precisely f0 of e. Okay, so that's what we have rewritten now, this alpha over k. Now we have called as f of k. The expression of f of k is given in the previous slide, and now we have seen that this is our f of 0. Okay, so now this is the one equation. Similarly, left hand side is also another function of k, right? Or equivalently, this is another function of e, so we can say that gk of or g0. Okay, so now to find the solution, what we can do, we can plot the gk and fk as a function of k in the same graph, and then the points of intersection will give the solution of these equations. Okay, because this is our f of k and this is our let's say g of k or minus g of k, depends on how you want to define it, and both are the function of your k. So we can plot the two functions as a function of k, and all the intersection point will be the solution of this equation. Okay, so this is another important lesson for you, that when we solve the problem for a free particle and the particle is an infinite potential box, we have got the exact solution. What it means by the exact solution, that the wave function for any nth state is written in one single expression and the corresponding energy. Okay, now as we have modified the problem slightly, we see that the mathematics becomes so involved. Okay, so the solution, or let's say the wave functions, are not so trivial that you can write in one line. Okay, so now to get what I have said it, all points which are kn, for which these two equations are going to be equal, gives the allowed values of k, or equivalently the allowed values of e or en. Okay, so then this is the way to get the value of e or en. Okay, so now here is a little bit mathematical trick that we are going to play. So this is the equation that we have written in the past. Okay, now what I have done, I have just divided this equation and this equation by cosine of kl. So when I divide this cosine of kl, I will get 1, and when I will divide this cosine of kl, I will get tan of kl. So that's what I have got, tan of kl. Okay, now I have also divided by k, so here I have got alpha over k, and here I have got unity. The same thing happened here. I have got alpha over k divided times tan of kl, and here I have got a plus 1. Okay, it's a mistake. It's a right, and now when we have to rearrange the whole thing, now I can rearrange the whole thing into this side, and now I can say that I have written into this following form, and now I can start expanding the whole thing. So this is this one. Now alpha over k is written into this following form, so this multiply by this, so this I have got it, and now when you substitute everything correctly, the whole equation boils down into this following fashion, like tan kl is equal to 2 times alpha over k divided by 1 minus alpha over k square. Okay, so this is the one we have got it, and now these are the values of our alpha and k. Okay, so as I said that these equation cannot be solved anymore on pen and paper or equivalently analytically, and we have to solve using the trick that you have used during your 10 plus 2 time, that if you want to know the solution of two functions, you have to plot the function, and wherever they intersect you get the solution. Okay, now this is what I have written from the previous slide. Okay, now the value of tan kl is written into this following fashion using the trigonometric relation, that tan kl is 2 times tan kl by 2 divided by 1 minus tan square kl by 2. Okay, and this is what I have got it. So now by doing a simple rearrangement, I can show that tan of kl by 2 is equal to alpha over k. This is the relation that I have said, and now I know also that tan 2 theta is 2 times cot theta divided by cot square theta minus 1, and I can say that this is my standard relation to take care of my minus sign. So this tells that my minus of cot kl by 2 is equal to alpha by k. So these are the two what I have got it. Okay, so far this is the one we have got from the previous slide. This is what we have got from the previous slide. This is our definition of alpha. This is our definition of k. Okay, now I can define k0. Okay, so my k0 is 2m divided by h cross square times v0, and then I can take the square root. Okay, so my k0 is square root of 2m v0 divided by h cross square. So then this is what I can say, that this is my k0 square minus k square is equal to alpha square. That's what I have, because k square is this quantity. Okay, so I'm trying to represent my alpha over k from this equation as I have said it. Okay, that it's square root of v0 minus e divided by e. I can just simplify the whole equation and I can rewrite into this following function. Okay, so now what we are going to do, we are going to plot a function, this one, because this is my alpha over k, this is another alpha over k, and this function which I am now going to call as f of kl is also alpha over k. So now I'm going to plot three functions as a function of kl by 2, because there is a kl by 2. Okay, and all the intersections points are going to give me the solution. Okay, and this is going to give me. So here is the plot. Let me say what is plotted here. So in the x-axis I have plotted half kl. Okay, and these lines which are continuously monotonically decreasing, these are different of f of kl. Why these are different? Because there is one value which is k naught here, and k naught depends on the v naught. So this first one is for different value of v naught, the second line is different value of v naught, third value is different value of v naught, and the fourth value is for the different values of v naught. Okay, and these are your tan of kl by 2 minus cot of kl by 2, tan of kl by 2 minus cot of. So you know these are the periodic functions. Okay, so when I have chosen the value of half k naught times l, okay, this is my k naught which is a dependent on the potential. Okay, when I have chosen 1, it will give me 1 bound state. When I have chosen 2, it will give me 2 bound state. When I have chosen this value, it will give me 3 bound state, and when I have chosen this suitable value, it will give me 4 bound states. So in this way I know that how many bound states I'm going to get, which depends on the value of v0. So as I increase the value of v0, it start accommodating more and more bound states. Okay, so this is the way that we have got it. Okay, so this is the first question: how many bound states does a potential well have? Okay, so this is you have to answer. Okay, now let's move on. So these are the three solutions for a particle in a finite box. Phi 1 in region 1 is a times e to the power alpha x. Phi 2 is c times sine kx plus d times cosine kx, and phi 3, which is a wave function in region 3, is h times e to the power minus alpha x. Okay, so if I plot it, these three wave function in three regions, the first function is increasing exponential. So this something looks like this one. We know how this wave function looks like from our previous knowledge of particle in infinite box. So this is something looks like this, because the wave function is supposed to terminate at the boundaries. That is something that we have seen it. So this is what we have plotted, and this is exponential decreasing. This is we have seen this one. So these are the three wave functions that we plotted. Now there is a very fundamental issue. There is a problem. The way that we have plotted, that the wave functions are not continuous at the boundaries, that you can see it. Okay, so phi 1 and phi 2 are not continuous at the boundaries. Phi 2 and phi 3 are not continuous at the boundaries. Okay, so now what we can do, as we have seen earlier, now we can write down the phi n of x. Now I have introduced subscript n, so everywhere subscript n, and all the coefficients, as I have shown you that all the coefficients I have presented a, c, d, h in terms of a. Okay, so that's what is done here. Okay, and now we have also defined which wave function falls in which region. So this is the wave function for x is equal to, for x is smaller than 0. This is in between x equal to or smaller than 0 and x x is greater than or equal to 0 and x is smaller than or equal to l, and this is the wave function for x larger than value of l. Okay, so this is the wave function that we have plotted. Okay, now if we perform the boundary conditions are supposed to be matched, so this is the smooth wave function that we have got it. Okay, which is shown in the solid blue line. Okay, so after taking care of the boundary conditions properly, this is the proper wave function. Now there is another very interesting thing that you do see, that the ground state wave function for a particle in a finite box looks like this one. Okay, so this is your inside well. Okay, this is outside well. My energy is smaller than potential, as I have said, so this is my V area, and now there is some finite probability of particle to be found outside the box or outside the well, because my wave function is leaked out here and my wave function is leaked out here. Okay, so particle well is not infinite, so the particle is not fully contained inside the well, and particle location extend to the classically forbidden region, because that's what you see, that if my particle has smaller energy than this wall, then there is no way that particle can come out this one classically. But quantum mechanically, what we have seen by solving Schrodinger equation for this problem, that this is the total wave function, and there is some finite range of the wave function outside the well. Okay, so this is what generally called as a forbidden region or classically forbidden region, and the particle has total energy less than this one. Okay, so these are the probability densities. So this is your psi 1 square, this is your psi 2 square, this is your psi 3 square, and in all the three cases you can see that the wave function is non-zero, or the probability is non-zero in the classically forbidden region. Okay, so there is a non-zero probability of finding the particle in region 1 and 3. So this is our region 1 and this is our region 3, and the probability decay exponentially outside the well, but it is non-zero, and classically this is forbidden. So this is what is called penetration of the wave function in the classically forbidden region, and that has a very immense applications. Okay, so now what we are going to estimate, the exponential tails of the wave function. Okay, so this is our wave function in this region. Okay, a times e to the power alpha n x. Now we can define the penetration length is reciprocal of your alpha n, because this from the unit or dimension wise, this alpha supposed to be inverse unit of x. So this we can define 1 over alpha n is equal to delta n, and delta n is your penetration length. Okay, so penetration length is proportional to the Planck constant, because your alpha is also proportional to the Planck constant. Okay, so now we can say that the value of your phi at delta n is equal to the value of your phi at x is equal to 0 divided by a. Okay, so then effectively the dimension of the potential well is L, this is L times delta n this side, and this is your delta n. So the effective dimension of your well is L times 2 times delta n. Okay, and then it's easy hand waving. Of course, the exact way is to find the value of energies by plotting your f, tan, and cot, and the intersection points are going to give you the energy. But there is an approximate way to find the energy by using our knowledge from the particle in an infinite box. The only thing what we have done it here, we have change the value of L, which is the length of box, from L to L plus delta N, and now this is the value comes out. Now the issue is that this delta N, which is dependent on alpha N, is again depends on E, because your alpha is V0 minus E, square root, it's proportional to this one. So this comes out some kind of recursive relation, that if you want to find out En, you have to find out delta N, and delta to find the delta N, you have to find out En, back and forth, back and forth. Okay, so now this is the comparison. Okay, so these are our wave function that we have learned when our particle was an infinite potential box, and these are the wave functions when our particle is inside the potential well. Okay, finite potential. Okay, so the first thing here, that your wave function terminates at the boundaries. Here the wave function have some finite probability outside the box. Okay, and these are the different wave functions. Also the energy level shrinks. So n is equal to 1 is a smaller energy for the same values of L, and the V0 here we have chosen 1 eV, and here we have chosen, or it's given that V0 is infinite. This value is again smaller. For n is equal to 3, the energy in this finite well is smaller than the energy in an infinite one, and the reason is simple, because if you see tentative energy, if this value is going to be large, your energy is going to be smaller. Okay, that's what you see it here. Okay, so now this is another question that you have to answer, so that no matter how small V0 is, there will always be at least one bound state. Write the conditions for the existence of 2 bound states and of 3 bound states. Okay, that's you have to bound. Now we can introduce semi-infinite one-dimensional box. So what it means semi-infinite? So in one wall we have infinite potential, where another wall we have a finite potential. So this is we call as a semi-infinite 1D box. We have a region 1, 2, 3 as usual. Okay, and then once you have a finite potential box, we do see that there is a probability of finding the particle is finite, whereas when you have infinite, there is a no probability that the particle can get out this side. Okay, now it's up to you to solve this problem by yourself as the way that we have done it. So I'm leaving this as an exercise.